Cool. So I guess you can see my screen now, right? Awesome.
Yeah.
So yeah, hi everyone. I want to talk about 3D digitization of faces, which means that we want to build 3D models of people from their images and videos. So as you can imagine, this has a wide range of applications. For example, in virtual reality, where we want to see a person from different viewpoints as we move around in the scene. And there are also applications in casual photography, where we might want to edit photographs after capturing them. So for example, we might want to relight them. And in movies, we often want to create new performances of actors, which could be difficult to capture in reality. So, for example, in the Furious 7 movie, several shots with the actor Paul Walker have computer-generated faces. So the shots you're seeing here are not actually Paul Walker. And in fact, he had unfortunately died in a car crash before these scenes were shot. Another example is this movie, The Curious Case of Benjamin Button, where the motion of the actor Brad Pitt was transferred to a digital model, which looks like an older version of him. In this particular case, to capture the motion, capture setup with multiple cameras was required, which is, of course, not very convenient. So what I work on is to enable building high quality digital models of faces from just image and video observations, which could be monocular, without the need for these controlled environments with scanners. So this problem has two steps. First is the inverse step, where we need to estimate the geometry and appearance properties of the face from the images and videos. And we need to make sure that the models we get out are easily controllable, because that's the goal in the end for all the applications. We want to create new performances. Now, once we have built the 3D models, we want to render them at a high quality for a very realistic performance. So I already talked a bit about traditional capture setups, which can include multiple lights and cameras in a controlled environment. So as you can expect, they're very expensive. And these are controlled environments, so they cannot capture just people going about in their day, so not really in the wild conditions. In addition, capturing videos is still very difficult. So in this talk, I will discuss some approaches for building 3D face models from just monocular images. And all we will need is a single image of the person. I think someone is not muted, so I get some echo. Okay, so on the rendering side, traditional approaches require high quality 3D assets.
Who was the senior vice president of product there, was like, hey.
Good, thanks. Right, so on the rendering side, traditional approaches require high quality 3D assets for photorealistic rendering, which is completely understandable. So the renderings can only get as good as the quality of the 3D models there, which is of course difficult in the monocular setting. So the reconstructions we get from monocular images are not that high quality. And here I will discuss a couple of methods which can work with the quality of the reconstructions we get from the monocular images and still result in photorealistic output. And these neural rendering methods are also efficient, so we can build interactive editing applications out of them, so like the one you're seeing here. So let's get started with monocular 3D reconstruction. And the task here is to estimate the 3D geometry, skin reflectance, the scene illumination, and the global pose of the face from a single image. So we want to figure out the full appearance of the face in 3D. Now this is an ill-pose problem. So we are in a monocular setting, so there are depth ambiguities. We do not know how far the face is going to be. And there are also ambiguities between the geometry and appearance components of the reconstruction. So we need a prior to solve this task. We first looked at this problem back in 2017 with this ICCV paper with collaborators from MPI, University of Luxembourg, and Technicolor. Right, so one option to solve this problem is to capture a large set of 3D scans and then use a supervised training method, which can estimate the reconstructions from the image, and we could train a CNN for this task. But there are no publicly available large datasets of scans. And as I explained before, it's also not very easy to build these datasets. So what we do instead is to rely on 3D morphable models, which also try to model the space of plausible 3D faces. And these 3D models are built from some very limited scans. The model we are working with only uses around 300 scans. So these 3D MMs are defined using a template mesh topology, and they're linear models, and they consist of some disentangled components. So there's first an identity geometry model. So here each parameter controls the identity-specific geometric deformations on the face. Then we have a model for the diffuse skin reflectance. So now each parameter is controlling the skin color of the face. And finally, there is an expression model. So now each parameter is going to change the expressions on the face by deforming the template mesh. And this does not include the geometric deformations. So the geometric deformations are separated out into two components, the identity and expressions. So the really good thing about this model is that it has these disentangled components. So there's a lot of control, which is what we would like to have in our 3D reconstructions. Another thing to note is that the number of scans used to build these models or these samples from these models themselves are not really sufficient for training a supervised learning method. And that's because the rendered images don't look very realistic. So there's quite a big domain gap. And also it's not really easy to figure out how to sample these models. For example, how to sample the expression component such that it matches the distribution of real images. So what we do is to use these priors in a slightly different way. But before we get to that, we need to first define some scene parameters. So as I said earlier, we also want to recover the global pose. And this is just 3 parameters for the rotation using Euler angles and 3 parameters for the global translation. Then we have the scene illumination. So this is described using spherical harmonic coefficients. And there's an assumption that the illumination in the scene is somewhat low frequency. So now we get this parametric representation of the scene. So given all these parameters, we can compute the radiance on every point of the face. With this parametric representation, we train a CNN now, which takes as input this image, and as an output, it gives parameters of the model. And because we know the model, we can compute the 3D reconstruction based on these parameters. Once we have the reconstructions, we can render it back to the image plane to get some synthetic renderings. And then we can design the loss function in the image space. So now we do not need supervision in the 3D space. So we do not need any data which has images and the corresponding 3D models. So that's very nice. The other advantage is that now we can train on images collected in the wild. We do not need to train on synthetic images. So in the end, the training data we needed was a data set of images collected in the wild. We just crop out the faces. We do not need any other annotations. And then there's this data set of small set of scans, which was used to learn the 3D morphable model. Right. So now we can take a deeper look into the renderer we are going to use. So the assumption is that faces are Lambertian surfaces. They're not really Lambertian, but that's the assumption. And the illumination is parameterized with spherical harmonics. And this leads to a nice closed form solution of the radiance, which is great. It's differentiable and it's efficient. This does mean that we cannot account for specularities, cast shadows, any indirect effects. The visibility is not differentiable, but as I'll show you, even with such approximations, we can learn reasonable reconstructions by training on in the wild data. And in the wild data, we do see all these effects. Yeah, an updated version of this renderer is publicly available, so you can check it out if you're interested. Now we have a synthetic rendering, so let's take a look at the loss function. This is quite simple. We first have a photometric alignment term. So for every vertex in the reconstruction, we look at how far the color is from the corresponding pixel in the image. We use an L21 loss, which helps a little bit with small outliers like small occlusions or shadows. Then we have some regularizers on the parameters of the 3D morphable model, which just says that the reconstruction should not be too far away from the mean of these models. Once it is trained at inference, we can perform reconstructions from a single image, and it is quite fast because the CNN is very lightweight. We used an AlexNet here. Right. So we can look at some results. So we can get reconstructions under different poses, expressions in different illumination conditions. They're not perfect, and in general, the reconstructions don't look very detailed, but they do manage to capture the overall shape and appearance of the face. So one of the issues in these reconstructions, the lack of detail and generalization is due to the 3D morphable model we used. So the 3D morphable model offers limited generalization of the output because it was trained on very limited quantity of scans. In addition, like scanning faces in the wild is difficult because, for example, it's difficult to capture facial hair, it's difficult to scan makeup, and that's why the scans in the dataset are quite limited in terms of their diversity. And this leads to some interesting limitations. So MOFA, which is the paper I just talked about, has this interesting failure case where the reconstructions tend to shrink around the facial hair just to avoid explaining that region of the image. Richardson et al. Trained a model on synthetic renderings from the model. And because the synthetic renderings doesn't have any makeup, at test time, when it sees a real image with a makeup, the model gets confused. So what we need to do is to build larger scale 3D models. And I think the only way to do that is by learning from 2D data. 2D data is really available at scale online, and not just for faces. If we want to start building models of other objects, we can easily find 2D data online versus for scans. We'll have to go ahead and use these setups to capture a lot of data. But this is challenging now because, as we looked at earlier, images have a lot of ambiguities. And that's why we started using the 3DMM in the first place. So what we did is to instead look at learning from videos. So videos are also available at scale online, but they also offer slightly more constraints. So this is what we explored in our CVPR 2019 paper with collaborators from MPI, Technicolor, Vallejo, Stanford. Right. So in this work, we decided to focus on the identity component of the 3D morphable model. So we said that, okay, we'll rely on a pre-trained 3D expression model, but for the identity component, we initialized it from zeros. There are no deformations, and all the deformations are going to be learned from the video data set here. So if you look in a video, we observe the face from multiple viewpoints under possibly different illumination conditions and expressions because the people are talking. So these are videos where people are giving interviews, speeches, and so on. So these are mostly videos of celebrities. So first, we can assume that the skin reflectance will remain consistent across each frame of a video. This is an approximation, so the reflectance can change with different expressions, but this assumption is not too bad if the aim is to get a coarse reconstruction of the face. Now for the geometry, we can decompose this into two components. So we first have the identity component, which we again assume to be consistent across each frame. And then we have the expression component, which is going to be different for each frame. So with that, we design a network architecture, which first has a per video network, which accumulates the features from each frame in the video. and predicts the identity, shape, and appearance parameters. So the network is designed to predict only one set of parameters by merging information from all the frames. So by design, the identity, geometry, and reflectance is going to be consistent for each frame. Then we have the Siamese per frame network, which estimates properties different for each frame. So these could be properties like pose, expression, and scene illumination. We have a learnable face model now. So this is initialized from zeros, as I said. Like last time, we're going to use a differentiable renderer, and we'll use this to define the loss in the image space. The loss function is also very similar to the previous setting. So we have the photometric alignment term. In this case, we also have a landmark alignment term. So we automatically detect some key points in the input image, and we manually annotate some semantically meaningful key points on the template mesh, and we try to align these two. The landmark alignment term becomes important now because the problem setting is more under constrained here. So we at least would like to define the region in which the region which the model should try to learn. So even though we're using videos which offer a bit more constraints, these are still not a perfect form of data. So the face deforms in each frame, and the range of viewpoints we're going to observe in the videos can be very limited. So we also needed some regularizers here. So first of all, we had a term which said that the reflectance should not change very often. So the change in reflectance should be sparse. And this basically says that local changes in appearance is mostly due to the shading effects and not reflectance. Then we said that the geometry should be smooth, and finally that the expression should not be too large. And with that, we trained our networks, and at test time, again, we can reconstruct from monocular images. So we do not need multiple frames of a video for inference. It can work with a single image. And now you can see that we can reconstruct faces with beards, some makeup, so in general more diverse than what we could do earlier. And the reason we can do this is because the model is now learned from these videos. So, and the videos, of course, include all these features. As a comparison, these are methods on the left which use a fixed pre-trained 3D trained from 3D scans, and that doesn't work very well in these conditions. And these results are temporally coherent. So I don't think that the video is very smooth on your end, but you can take my word for it, and then you can later go on and check these out in the project page. So I mean, we focused on beards and makeup because these are things which made existing methods fail very easily. But there are also other advantages. For example, the original 3D morphable model was trained only on Caucasian people, and it turned out that it didn't work very well. The reconstruction methods which were using those 3D morphable models did not work very well on people of other races. And when we started training on 2D data, we realized that the model started to perform better and like equally well on all races. The 2D data itself could have its own biases, but seems to be much better compared to the 3D scans data set. Right, so in this method, we still relied on a pre-trained expression model, but we have since extended this approach. So now we can learn a 3D morphable model from 2D data using just a single template mesh. And we do not need the pre-trained expression model now. So disentanglement becomes a bit more challenging now. So earlier what we did was we said that whatever is not expression is identity, and expression was defined using a pre-trained expression model. But now that we do not have either of the expression and identity models, and we still want to separate these out, what we did was to use a data set of images with neutral faces. So everyone in the data set had a neutral expression. And this is quite easy to collect, and there are data sets like these out there. So we took that data set and we said that during training for those images, all the deformation should be due to the identity component, and the expression should be zero there. So this just helps that the expression doesn't start to overcompensate for the identity as well. And in addition, we have a pre-training strategy where we pre-train the identity model first, and this seems to help quite a bit with disentanglement. Here you can see the visualization of the model now learned only from 2D data, and the different modes of these deformations are disentangled and reasonable. So I think this is what you would expect plausible deformations of the face to look like. Right. Just to demonstrate why disentanglement is useful, here we can transfer the expressions from people on the left to those on the top. So this is like the example we saw of Brad Pitt's motion being transferred in the curious case of Benjamin Button. This is, of course, at a lower quality, but again, in a much more constrained setting. Right. So now we have this nice controllable reconstruction method, which is very nice, but there are several limitations. So we are only modeling the inner face region. So we are leaving out the hair, ears, neck, torso. And even for the inner face region, we made several approximations. So we said that faces are diffuse, they're Lambertian, but they're not. We assumed that the reconstructions are smooth. Our priors made sure that the reconstructions are going to be smooth. So we did not try to model the high frequency components like wrinkles, for example. So we are far from photorealism here. And now I want to talk a bit about how we can get closer to photorealism. So we looked at this in last year's CVPR paper. So at that time, we were all very amazed by the impressive quality obtained by StyleGAN. We're still very amazed by it. So StyleGAN can generate very high quality photorealistic images by sampling from its latent space. So this is also a parametric face representation. There is this one-dimensional latent vector from which we can sample, and then the output is a final portrait image. And this parametric model includes everything which our 3D model could not capture, like hair, teeth, torso, even the background. The problem is that StyleGAN does not have the semantic control which our 3D model had. So the 3D model which we're looking at, it has these nice controls, very well defined, and that's very nice, but this was not photorealistic. So the goal here was to build a generative model of portrait images where we preserve the synthesis quality of StyleGAN, but we also allow for 3D controllability using the 3D morphable model. And we did this by learning a mapping between the parametric spaces of these two models. So both the models are pre-trained and fixed. All our model does is build a mapping between these two spaces. And the method also does not require any additional training data, so it only relies on random samples from these models for training. This is how the method looks like. So the input is a StyleGAN code vector, which is going to be the input to the StyleGAN generator. And the target 3D control parameters are also used as input, so both are one-dimensional here. There's a simple two-layer MLP, which computes a new code vector, which corresponds to the target image. And the target image should be the same image as the input StyleGAN image, except that the control parameter, according to the control parameter, it should have been edited. Right. So we train separate networks for the different components, and I will explain how we do it for the pose component, but for the others, it is exactly the same. So we basically want to enforce two properties in the output of the network. So first, we want that the face in the output should be in the target pose. So it should have been edited as specified in the target control parameter. And additionally, other properties like identity, expression, illumination, everything which is not pose should be the same as in the StyleGAN code, which was used as input. And these properties are all familiar. We have a method which can estimate the full appearance of the face. So all these properties are defined in the 3D morphable model. So that's what we do. So we now estimate these properties directly from the StyleGAN code vector. So this is very similar to the reconstruction method I talked about earlier. But what we do now is that instead of using the image as input, we use the StyleGAN vector as input into this differentiable face reconstruction network. And it's a simple 3-layer MLP, which is now going to predict the parameters. And it's trained in exactly the same way as I talked about earlier. So there is a differentiable renderer which goes and checks the quality corresponding to the with the corresponding images. But now this is already pre-trained and fixed, the differentiable face reconstruction module. And when we are training this mapping, this RigNet mapping, we're going to use a pre-trained face reconstruction, and we're going to get these parameters as output. And after that, the loss becomes simple. So now we have the information about the pose and the output. So we can say that, okay, that should be the same as the target parameter, and every other parameter should be the same as the input StyleGAN code. One detail is that we try to implement these losses directly in the parameter space. So an L2 loss for each component here. But that did not work very well because it's difficult to carefully weigh all the different losses. So we'll get 4 or 5 L2 terms, and it was getting difficult to weigh them because similar L2 errors in different components can lead to very different perceptual difference in the image space. So in the end, we ended up using a loss function, which was also defined in the image space using the differentiable renderer. And you can go check it out in the paper if you're interested. Right. We also added a reconstruction loss, which basically said that, okay, if the target pose is the same as that in the input StyleGAN code, the output should be the same. So it helps in anchoring the training. And with that, we can get some nice results. So here there's the 3D mesh on the left and the output of the method. So the output is the StyleGAN code, then it goes to the StyleGAN generator, and this is what we get in the end. And these are all images sampled from the StyleGAN latent space. And even though the mesh is incomplete and smooth, the whole head has to move because StyleGAN can only give as output like realistic images. You can do the same for expressions. And finally, we can also change the illumination. And again, you can see that the only signal the training method gets is that on the mesh, the lighting has changed. So it sees that on the face, the light should move, and the network extrapolates from that and figures out that, okay, the best way to do that is to also globally change the illumination. There are also some limitations here. So we do not manage to transfer all the expressivity of the 3D model to StyleGAN. In-plane rotation does not work because the training data set was cropped in a way that all these in-plane rotations were canceled out. And some asymmetric expressions can lead to very results with a lot of artifacts. We also looked at the distribution of the parameters in the StyleGAN generated images, and right. And you can see that like this is the in-plane rotation and this is non-existent, which makes sense. This is the distribution of expression parameters, and it only has, there are only 2 components here which are mostly activated, and both of these components correspond to mouth open expression. And this also, I think, is this makes sense because StyleGAN is trained on Flickr HQ, so images collected from Flickr, and in static images, people tend to smile and laugh. So there's not a very wide range of expressions which are captured in datasets of static images. So this makes sense. And because we train our mapping network on random samples from StyleGAN, it also makes sense that when we try to edit other expressions at test time, it does not really work well. So now we managed to get some nice 3D control over StyleGAN generated images. One advantage is that it's kind of a unified method. So existing methods for pose editing, expression editing, relighting are all designed very differently with different capture methods, different data sets, different network designs. And it's nice that now we can start to use a pre-trained unconditional generator and turn it into a conditional generator based on the target application we have. And it does not require very different methodology. Personally, I really like that I don't have to train a very large GAN from scratch because training takes a long time. And both of these numbers are on a single GPU, so single Volta. Right. So now we can embed real. Now we can control StyleGAN generated images, but what we really want is to edit real images and to build 3D models of people we know we capture in images. So for that, we need to figure out the StyleGAN latent code which correspond to the images we have, and for that we need to embed the given image in the StyleGAN latent space, and that's what we looked at next. And here we are going to design an embedding method, which is called pi, which computes latent vectors for real images, such that they can be edited using StyleRig. So there's a clear goal here. The nice thing to try is to optimize for the latent vector such that the output of StyleGAN matches the input image. And the synthesis term here includes an L1 and a perceptual term. So this works very well. The reconstruction is really close to the input image, but when we start editing this latent code, the output quite often has a lot of artifacts. So in this particular case, we also have access to the editing method. We know that in the end, we want to edit using StyleRig, so we can simply add that in the optimization loop. It's differentiable, and we can have like clear constraints based on that. So that's what we do. We add the previous editing method here. So edit parameters are the target control parameters, and RigNet is the MLP, which is going to transform the latent vector based on these edit parameters. So the first thing we do in the optimization loop is to add a face recognition term, which says that after editing, the face should be of the same person as in the input. And this, at this point, most of the artifacts from the results are gone. So the recognition network does not really recognize the person if the image has a lot of artifacts. So that's great. Then we also add the editing terms which were used to train StyleRig. And this helps in improving the accuracy of editing. So it kind of ensures that the optimization method does not cheat by trading off the recognition and editing terms. So it does not like minimize the recognition error at the cost of editing accuracy. And so this is an optimization framework. Everything is fixed. The only thing we're going to optimize for is the latent vector of StyleGAN. One important aspect here is the latent space we choose to optimize in. So there's a latent space Z in StyleGAN, which is randomly sampled from a Gaussian during training. And this space is not very suitable for embedding real images. At least I did not manage, and I have not seen any other paper which has managed to do that well. Then there's a mapping network which maps these Z parameters to W vectors. Now this space is better disentangled, it's better for embedding, but it still does not get to very high quality for embedding. So what this W space is then broadcasted to the different layers of StyleGAN, and this broadcasted space is called W+. So most methods choose to learn or optimize in this W+ space, where each individual W vector for each layer is allowed to be a different W vector. So there's no constraint that all the values have to be the same across the layers. So what we observed that directly embedding in this W+ space leads to very high quality reconstruction, but can lead to poor quality editing. And on the other hand, if we choose to optimize in the W space, we get very good editing quality, but the reconstructions don't look that nice. It's difficult to match the identity of the person in the reconstruction. So what we do instead is to use a hierarchical optimization strategy where we first embed in the W space, then we use this as an initialization and then refine it in the W+ space. And this seems to work well. We get high quality reconstruction as well as editing. And you can see the difference in quality here. So in the middle is this directly optimizing in W+, and on the right is this hierarchical optimization. The interesting thing here is that the artifacts are mostly in the region where we don't have any 3D model. So in the face region, we have strong constraints which says that, okay, the face should look more or less like what the 3D model asks it to look like. But for the hair, for the ears, there is no such constraint, and it seems like most artifacts happen in those regions. Some more results. Can edit the pose and illumination. So they look very much like the results I showed earlier, with the difference that now this works on real images. You can also do expressions like last time, and this approach shares the same limitations as in there's limited expressivity. All it can really do is to open and close the mouth. Right. So at this point, we have used a single template mesh, a dataset of videos, and a dataset of high quality images in order to build nice, controllable, and photorealistic models of people from just a single image. So the mesh and video dataset were used to create this nice 3D morphable model with disentangled controls. The image dataset was used to train StyleGAN, and then we built a mapping between these two latent spaces. So hopefully at this point, you're convinced that we can build nice digital human models in a self-supervised setting without the need for a lot of 3D supervision. Like one thing is that the information in this slide is not completely correct. So we also used a face recognition term in the last project, which was trained on a different data set. But I think that you could also possibly train the face recognition network on the dataset of videos which we're using here. So it's not completely factually correct. So just take this with a pinch of salt. But I do think that this is, in general, this point I think holds true. So how can we get to higher quality 3D models? So first of all, we'll need higher quality 3D reconstructions, which are more detailed and complete. So we should not be limiting ourselves to modeling a small region of the face. We will need better appearance models. I focused on editing static images, but looking at dynamics and editing videos is also interesting. Another thing which I did not cover is person-specific behavior. So right now we can change the expressions of a person, but everyone has a different way of smiling, of expressing themselves, and that is not captured. So if everyone opens their mouth in the same way, it might not really look very realistic. We will also need higher quality rendering networks to fill in the gap for photorealism. But I do think that with time, the 3D reconstructions will get better by themselves, and probably we'll need less and less of networks which operate directly in the image space to fill in the gap for photorealism. So I think ideally in a few years, our 3D reconstructions themselves will be very photorealistic. So I want to very briefly talk about some recent efforts towards getting to higher quality reconstructions. And I wanted to talk about building full head models. So you've seen this video many times now. It's only face region. What we want to get to is to capture the full head region, including hair and ears and everything. So for the face region, it makes sense to use a fixed mesh template, to use a linear model, but these design choices might not be very well suited when we start modeling the full hair, for the full head, including hair. And this is because the deformations are going to be larger and they might not be as smooth as here. But we have seen nice parametric models of shapes like DeepSDF, which can model objects with even different topologies. So the shape representation here is a sign distance function, and it's parameterized using an MLP. The input to the MLP is an object code for each object in the training data set and the XYZ position in space. And then the network tells us how far is this point from the surface. And the object codes are also learnable during training. So we wanted to use a similar representation for learning 3D morphable models. And there are several advantages here. So we do not need to define a mesh template. We do not need to perform dense registration between all the training shapes before training. So that's good. But we also have some challenges. So we want to model the appearance of the head. And we want some semantic control. So we want the good old compartmentalized control like we had in the older 3D morphable models. So this is not present in deep SDF-like methods. And in addition, we would also like some correspondences between the different instances of the head, because as I said earlier, like the image fitting algorithms uh, are greatly helped if we have access to some sparse correspondences. So this is what we tried in our upcoming CVPR paper. And in this particular case, we're trying to learn from 3D data, from 3D scans. So first of all, we went ahead and recorded some people in a multi-view static scanner. We asked everyone to perform a fixed set of expressions. We gave everyone a couple of caps, and then we used photogrammetry to get 3D scans for each of these settings. Then we have our network architecture. So first we have a shape deformation network where we provide the 3D coordinates, and this time some semantically meaningful latent codes as input. And the shape deformation network now deforms this 3D point into a different space, which is a reference space. And there's a reference shape network, which gets as input the deformed point, and it tells us now how far this point is from the surface. So what the network is doing is learning a reference shape, and it's also learning how to deform this reference shape in order to get to the shape, to the final shape. Then we have a color network, and this again gets some latent vector. And interestingly, the color network gets the input coordinates in this reference space. And this is very important for disentangling the shape and color components. So because they're in different spaces, it's very easy to disentangle them. But if both were in the deformed space, it would not have been possible to do this, because that's not there in the data. So we don't have like two shapes with the same color or one shape with two different colors. So it's not trivial to do this, I think. Right. Every network is an MLP here, so that's quite simple. And the loss function is an L1 supervision for the for the SDF and also for the color. So the network predicts the color of the closest surface point. So the color is everywhere and it's of the closest point on the surface. Then we annotated some sparse correspondences on each training shape, and we have a loss which just enforces that. And then we have some regularizers, which are mostly borrowed from the deep SDF paper. So we do not need dense correspondences, but because we have the separation between the reference shape and this deformed space, we can compute dense correspondences at test time. And also interestingly, even if we do not have the sparse correspondences during training, even then the dense correspondences the network gives us are quite reasonable. It's just that by adding the sparse correspondences, the quality improves. So after training, we can take a test scan and optimize for its latent vectors, and then we can edit these latent vectors by changing these latent dimensions for identity, for color, also for expressions. And you're also seeing the visualization of the dense correspondences here. This is expression, and we also see deformations of the hair. So we cannot do a lot of different deformations. What we can do is to make the hair shorter, longer, and we can add one of these two caps. And because we have these dense correspondences, we can have some interesting applications. So for example, we can paint a segmentation map on any scan and then transfer them to every instance of heads generated from the model. And we can do the same with some key points. And as I said, this would be very nice for image fitting algorithms. So that was full head models. And now I will just show a teaser for learning better appearance models. So this is also very recent work, also with some collaborators from MIT. And Here, instead of saying that faces are diffuse, we try to learn a better reflectance model using light stage data sets. So we have images of people captured under different light sources and from different camera viewpoints. And we learn a material model such that we can capture most of this appearance. So we do not assume any existing BRDF model, and we really try to learn everything of the reflectance model. And this is again controllable, so we can change the light source now. We are also not restricted to smooth environment maps. So what you're seeing here is a movement of a point light source. And we can use this model to reconstruct from monocular images. So we do get reconstructions which are more detailed now. You can see subsurface scattering, self shadows. So there is quite a bit of progress in that direction as well. So I showed these methods which can learn higher quality models using controlled data setups with these multiple lights and cameras. But I still think that learning from 2D data is absolutely essential. So the 3D data sets in these problems were far from perfect. So for example, in the full head case, we mostly scan students in our university, so the demographics is very skewed. And it would really take a huge effort to scan a large and diverse set of population. And we might not even manage to do this if you're scanning in a single place, in a single city. In the reflectance learning paper, we relied on this nice light stage data set, but there everyone was scanned with their eyes closed in a neutral expression. So we did not manage to learn the appearance of eyes. So even though these data sets are very nice and they help us build these nice representations and training regimes which tell us what higher quality models could look like, I do think we have to go back to 2D data and utilize that for generalization. Um, and especially if you start looking at modeling other objects around us, not just faces. So for example, if you start modeling animals, I think it will be difficult to convince the tigers to stay still in a static scanner. I think it's already difficult to convince humans to do that. So I think that in the future we're going to see photorealistic and animatable models of objects all around us learned from just community data. And with that, I'll end my talk. Thank you.
Thanks a lot, Ayush. That was great and interesting. We have time for a few questions if anybody has questions. So I guess I can start. I have a question about the work where you like learn these deformable models with SDF. So I'm not sure why do you need like this reference space? Is it because the faces are scanned from different positions or orientations? Or
So there are two motivations there. One is that so we wanted to disentangle the color and the shape, the color and geometric deformations. And if we don't use these two different spaces, that becomes very difficult. So now we are saying that the color is being like the change in color is always happening on a reference space, and that reference shape with the changed color is now going to be deformed according to the particular instance of the scan. And this becomes very difficult. I don't even know how to do this if we don't have this reference shape here. And the other reason is that we wanted dense correspondences without actually having to supervise with dense correspondences. And this by design gives us some dense correspondences.
I see. Okay, thank you.
I'll ask a question. Hi, that was an excellent
Hi.
talk. Really neat work.
Thanks.
In your CVPR 2021 Learning Complete 3D morphable models, you had a slide about taking identity from one person and other variables like pose, expression for another person. It seemed like maybe there was some bleeding through of the identity from the person whose pose was taken. Can you go to that slide and talk about that?
Sure. Wait. Oh, this was quite far back. We're almost there. This one, right?
Yeah. Yeah, so you're taking the identity from the top, but the pose and expression from the left, but you sort of have like the lips of the person on the left seem to be bleeding into the first column, for example, first row, first column.
That indeed looks like that. Like the color of the lip seems to be more closer to the person on the
Maybe
left.
the eyes as well.
The eyes, I'm not too sure about the eyes because the eyes are also asymmetric in the video, but that is indeed true. So we do not actually transfer the reflectance parameters from the video. So it is really the reflectance from the top image, but it could just be that this was not very accurate and the lip color was somehow inaccurate in such a way that it looks like this person. But I'm not too sure about that. I'll probably have to go and check it out. I think you might be right, but yeah, I'll have to probably check it again. But I think at this point, I think I'll say that it's just a bit inaccurate and it ends up looking similar to that woman.
Yeah, do you know what it might be that sort of allows that to come in? Does it mean just is it actually bleeding through, or you think it's just an inaccurate, slightly inaccurate estimation of the reflectance parameters from the person on the top?
I think it's an inaccurate prediction. I don't think there's an easy way for it to bleed through. So the identity geometry can bleed through because if the disentanglement there is not very nice, what could happen is that the expression deformation could also be doing the identity deformation, but that's for the geometry. For the appearance, I think that's not very easy. So I think it is really an inaccurate prediction.
Okay, so the shape of the lips could bleed through, but the color shouldn't, basically.
Exactly.
I see. Thanks.